Hello, everybody. It is just about 7 o'clock, so I want to make sure that we get started on time. Thank you so much for joining us today for another Sky Tonight show with our wonderful Dr. Lisa Will, the fleet's resident astronomer and a professor at San Diego City College in physics and astronomy. If you have not joined us before for Sky Tonight, welcome for your first one. I hope you will have a wonderful time. If you have been with us before, welcome back. We're glad to have you again. You know how this will work. Dr. Lisa will give a presentation. She is going to lead us through what the sky looks like this month. So if you would go out into your backyard or on the street and watch the sky tonight, she will tell us exactly what to look for and what we will see. And after that, she's going to explain to us the life cycle of stars, because that is tonight, this month's topic. And then we have a Q&A for you all. So if you have some questions, Lisa will be here to answer them. And since this is a webinar setting, the way that you ask questions is you use the Q&A function, which is in your little command bar. I think that's what it's called. It looks like two little bubbles. And you just hit that, it opens a window, you can type your questions and we will get to them. You can type them anytime. So if you don't want to forget your question as it pops into your mind, just type it in there. I'll keep an eye on it, but just remember we might not get to it until we get to the Q&A part. And Karen, thank you very much for the compliments, for the music. That was actually from an IMAX film that we showed at the Fleet Science Center. It's called The Living Sea, and the music was by Sting, just in case you were wondering. All right, thank you so very much. And with that, I'm going to turn it over to Lisa. Lisa, take it away.
All right, thank you so much, Andrea, for the kind introduction, and welcome everyone. It is good to have you here. Just so you're aware, there are a couple dogs in the background, so you might actually end up hearing a dog from time to time. I apologize in advance, or maybe not. They're cute. All right. So as we do every month when we do the Sky Tonight program, we start off with some current events. And I thought I would mention that the Nobel Prize in Physics for this year went to endeavors in astrophysics. It went to Roger Penrose for theoretical research in black holes, and to Reinhard Genzel and Andrea Ghez for the discovery of the supermassive black hole at the center of our galaxy. I wanted to, particularly for Andrea Gez's research group, she is a professor at UCLA, and their research group produces amazing graphics that if you've been to the Sky Tonight show before, you've seen me actually show some of these. So for example, this is one of the major research products from her research group. Every one of the balls in this image is actually a signal from a star near the galactic center. That white star in the center of this image is actually the physical location of the galactic center. And what you might have noticed as this animation is playing, you can see the year up at the top right. And you'll notice that some of these stars are getting really close to that thing in the galactic center. They're just kind of whizzing around really quick. Now, to give you a sense of perspective, this animation is taking place over a period of just about a couple of decades, right? Well, you know, Saturn takes 30 years to go around the sun once. And so these are stars moving over large distances in the center of our galaxy. So whatever is tugging on them must have a lot of mass, must have a lot of gravity to get them to move that fast. And so it's this sort of data that allowed Andrea Ghez and her research group to determine that the estimated mass for the supermassive black hole at the center of our galaxy is about 4 million times the mass of our sun. And it would be wrong of me not to mention that with the awarding of this Nobel Prize in Physics, you can now count the number of women who have won the Nobel Prize in Physics on 4 whole fingers. 4 whole fingers now. Maybe one day we'll get up to using 2 hands. Let's continue on from there. There's a interesting moment in a spacecraft mission coming up this month, and this one hasn't gotten a lot of news, but this is an absolutely fascinating mission. This is the OSIRIS-REx mission. And this is an artist representation of what's going to happen on October 20th of this month. So OSIRIS-REx has been in orbit around the small asteroid Bennu gosh, almost 2 years now. And what it's been doing during this time is it has been taking a map of the entire small asteroid, because what it's going to do on October 20th is it's going to approach the surface of the asteroid and reach out and take a sample of it. And so it spent the first year or so of observations mapping the entire asteroid, trying to look for a good landing site, because the way this sample collection will happen is that the spacecraft will lower down to the surface of the asteroid, and then it's actually going to fire some nitrogen gas jets. And the jets of gas are going to kick up some debris, and that debris is going to get collected. And so what the astronomers had to do was actually figure out where would be a good site where we could actually kick up some soil, some dirt, and get it collected. And what was interesting about this one is that this asteroid turned out to be a lot rockier than expected. And what I mean by that, okay, like asteroids are chunks of rocks. You might be saying, like, what do you mean by that? Its surface has a lot of sharp, jagged boulders all over it. So we eventually settled upon this site called Nightingale, which has a large region of what looks like fine-grained material that this sample collection can achieve. But to give you a sense of scale, if you think of this spacecraft as being around the size of a bus, it's only going to be navigating the size of a couple of or not a bus, a large van, or maybe a bus, something on that size, right? It's only going to be navigating the size of a handful of parking spaces. That's how much room it has to maneuver in between the boulders. But listen for this on October 20th, because hopefully it will successfully sample some asteroid material. And if it doesn't work this time, it will they'll get a chance for it to happen again. And then this is a sample return mission. So unlike when the rovers on Mars, they're chemical laboratories that we've sent to Mars. In this case, we're picking up material, and then in 2023, the spacecraft is going to fly by Earth and shoot this little pack back at the Earth for us to pick up. So this is a sample return mission of asteroid material. And like I said, it will return to Earth in 2023 if all goes well. This is an image of Venus, a combination visible light and infrared image of Venus, so that you can see Venus's cloud structure. And I'm mentioning Venus's clouds because you may have heard of the discovery of the chemical phosphine in Venus's atmosphere last month. And what's interesting about this is that phosphine here on Earth we find being made naturally only by biological processes, whereas on larger planets like the gas giants like Jupiter and Saturn, the conditions in their interior could make this material or this chemical naturally without needing a biological process. So there is some speculation. Now, I want to say the scientists who wrote this paper didn't say aliens, they didn't say life, but they did mention that this is a very intriguing discovery, because here on Earth, which is almost identical in size and composition to Venus, I mean, our atmospheres are different, but in terms of types of planets that we're both terrestrial planets of a similar size, that it would be fascinating to find out what's causing the chemical phosphine to be created in the clouds of Venus, because that's new chemistry. So the scientists themselves said, could be life, probably not, but you might have seen some could be life headlines, right? But in any case, this is a really fascinating discovery in the clouds of Venus. So that is a very quick overview of some of the highlights of astronomical news over the last month. Now let's get started with a tour of the sky. So what we've done is we have set the sky to what it would look like at around 8:30 tonight. So basically, if you get excited and want to go try to take a look at the sky and it's cloud free where you are after the show, you can go outside and take a look. Now, you're not going to see these images up in the sky, but I wanted to give you a feel for what the mythological creatures are that are up above you. So when we take a look at this here on the screen, south is at the bottom of the screen, north is to the top, east is to the left, and then west is to the right on your screen. And so these are the mythological interpretations of what you probably put together as stick figures on the sky, right? Our brain likes to connect the dots when we look up at the sky. So what we're going to do now is we're just going to take a tour of some of the highlights, not every single one of these constellations, but we're going to talk about some of the highlights here. So this is actually what you see when you go outside and you look at night. And then you can see that there's sort of a band of light going from the southwest towards the north across the sky. And that's the Milky Way, which you can see if you're somewhere without a whole lot of light pollution. And if you follow the Milky Way towards the north, the first bright star you come across is the star Altair in the constellation Aquila. Aquila is the eagle, which is thought to represent the bird who carried Zeus's thunderbolts in Greco-Roman mythology. Now, Altair is an interesting star astronomically. It is relatively close to us. And what I mean by that, it's only about 17 light years away. A light year is the distance that light travels in a year. And so when you take a look up at Altair in the sky, you're seeing it not as it is, but rather as it was about 17 years ago. Now, believe it or not, you don't have good depth perception on the sky. And so remember that Altair is only about 17 light years away, because if I continue north along the Milky Way, the next bright star I see is the bright star Deneb at the tail of the constellation Cygnus. So basically the way this planetarium software is, it's covering the brightest star in Cygnus. So imagine there's a bright star underneath the G right now. Now, that bright star has about the same brightness as Altair does in the sky, but Deneb is about 3,200 light years away. So if you go outside tonight and you look at Deneb, you're not seeing it as it is, but rather as it was about 3,000 years ago. So I like to mention that because we're so used to having ideas about depth perception on like if things are the same brightness, they must be the same distance. If they're the same size that we perceive them at, they must be at the same distance. Stars aren't like that. In fact, most of the closest stars to the sun are actually faint red small stars that we can't even see with the naked eye. There are stars close to us that we can't see, and then there's stars really far away that we can. So no good sense of depth perception on the sky. Now, if you look kind of to the right or to the west of Cygnus, you'll see a bright star, and that is the star Vega in the constellation Lyra. Lyra represents the harp of Orpheus from Greek mythology. And its brightest star, Vega, is the fifth brightest star in Earth's nighttime sky. It's about 25 light years from our solar system, and it's a bright white star in our sky. And those three stars together are so prominent in the late summertime and early fall sky that they're called the summer triangle. And so if you've noticed a bright triangle of stars overhead that take up a big chunk of space on the nighttime sky, you've been seeing the summer triangle. And it'll be getting lower and lower in the sky at this time of night as we go deeper and deeper into fall. Now let's see some other constellations. Here we have Hercules, which is the fifth largest of the 88 constellations that modern astronomers use. The brightest star in Hercules is called Kornephoros. It is a word that comes from a Greek term that means club bearer, because Hercules is usually shown carrying a club above his head. And then Hercules, as part of his heroic adventures, encountered a dragon named Ladon, which is probably represented up on the sky here by the constellation Draco, the dragon. The most famous star up in the constellation Draco is the star Thuban, which about 5,000 years ago was actually the North Star, whereas what we call the North Star now is the star Polaris in the constellation Ursa Minor. And it's called the North Star because if you were standing on the geographic North Pole of the Earth and you pointed straight up, you would be pointing towards Polaris. But if you would have done that about 4,000 or 5,000 years ago and pointed straight up, then you would have been pointing at Thuban. And that's because the Earth wobbles, it precesses on its axis over a period of about 26,000 years. Some other constellations of interest up here in the northern part of the sky. We have Cassiopeia, who represents a mythical queen. Um, Cassiopeia is easy to find in the northern sky because it looks like a prominent W or an M, depending on your perspective. And the 5 stars that make up that letter, they're actually all fairly bright. So even from a city like San Diego, you can actually see it quite easily. Now, Cassiopeia represents a mythical queen, and her mythical counterpart king is Cepheus, and he is also up in the sky, in the northern part of the sky. And they had a daughter, Andromeda. And so um, she was put up in the sky after being rescued from Cetus the sea monster. Uh, by Perseus, who was another hero from Greco-Roman mythology. Now, why did she need to get rescued? Because her parents boasted that she was so beautiful, she was more beautiful than the daughters of the gods, which upset the gods. So you don't do that. And so they punished their daughter, and she was rescued by Perseus, which is also a constellation, but it's not quite visible at this time of night, at this time of year. But when Perseus did rescue Andromeda, he did so with the help of his winged horse, Pegasus. And Pegasus sprang from the body of the Medusa, the Gorgon. And what you might notice in Pegasus, the constellation, is that there's something that looks like a big square, which astronomers refer to as the Great Square in Pegasus. And just like there's a triangle in the sky, this is a fairly noticeable square, large square in the sky with 4 stars of relatively equal brightness bounding it. So go give it a try to see if you can find that later tonight. And then we've been ignoring the southern part of the sky. Down here in the southern part of the sky is Pisces Ostrinis, the southern fish. It is a relatively small and faint constellation, but its brightest star, Fomalhaut, is the 18th brightest star in the nighttime sky. The name comes from an Arabic phrase that means the mouth of the fish, and that star is located about 25 light years from our solar system. Now, when you take a look at where it is now, you need to look very low on the sky, towards the southern sky to see it. But if you're looking south, so if you're standing normally, you're not looking way up above you, but standing normally looking towards the southern horizon, Fomalhaut will be the brightest star you see in that direction. And although you might not have heard of Pisces Ostrinis, it's actually one of the 48 constellations that was first cataloged by the astronomer Ptolemy in the 2nd century. And a lot of those 48 constellations that he cataloged almost 2,000 years ago at this point are still used by astronomers today. This constellation has its roots in Babylonian culture. It was associated with a fertility myth of a particular Syrian fertility goddess who fell into a lake near the river Euphrates and was rescued by a large fish. And so adding a different bit of mythology up on the sky for you, a story you might not have heard. Now there are some constellations up in the sky, and like Pisces Ostrinis, I bet you thought, hey, I've heard of Pisces before, but it's not Pisces Ostrinis. You're used to Pisces. That is a sign of the zodiac. So where did the signs of the zodiac come from? Well, they come from this green line on the sky, believe it or not. What does this green line show you? Well, you might notice that there are months of the year located along this, and this is the ecliptic path of the sun. This is where the sun is on any given day of the year. So since I have this set for 8:30 tonight and the sun set earlier this evening, you'll notice that October is well below the western horizon at this time, as it should be. So on any given day of the year, we know where the sun would be. And so because the sun is so important, it gives us the vast majority of the energy that we have here on Earth. So we consider the sun to be incredibly crucial. The constellations that the sun passed through were considered to be incredibly crucial, and those gained particular cultural significance, and those are the signs of the zodiac. Now, the first sign of the zodiac, though, that I'm going to mention is Ophiuchus, which you probably haven't heard of unless you've been here at the show and I've been telling you there's 13 signs of the zodiac all along. And so Ophiuchus is a sign of the zodiac because the sun passes through this constellation the first week or so of December. Ophiuchus is a serpent bearer, and its brightest star is a star called Rasalhague, which is located about 49 light years from our solar system. We're going to follow the zodiac from west to east across the sky. And the next sign of the zodiac that we have here is the constellation Sagittarius, which is an archer. It actually depicts a centaur, which is a half human, half horse from Greek mythology. To me, like you see, it looks like it has like a long tail or something off to the east. You don't really see that part with the naked eye from a city like San Diego. But you do see something that looks like a teapot in the sky. And so lots of times astronomers refer to this as the teapot up on the sky. And the spout of the teapot or the arrow of the archer points towards the widest part of the Milky Way on this screen. And that's where the center of our Milky Way galaxy is located, about 27,000 light years from us. And so when I showed you the images of the stars orbiting around the black hole at the center of the galaxy, when we were talking about the Nobel Prize in Physics a little while ago, the teapot's pointing to where that is. And so people always ask, can you show me where a black hole is on the sky? And I'm like, I can't show you where any particular black hole is on the sky, but I know there's a supermassive black hole of about 4 million times the mass of the sun. And right there with the widest part of the Milky Way. And so this is located, the galactic center is located about 27,000 light years from our solar system. Our galaxy is about 100,000 light years across. And so we're located about halfway out from the center to the edge. The next sign of the zodiac going over to the east is Capricornus, the sea goat. It looks just kind of like a triangle on the sky, kind of a deformed triangle on the sky when you can find it. It is the second faintest of the zodiac signs and a relatively small one in total area. And it doesn't really have a whole lot of bright stars. Its brightest star is the only one that is easy to see in a metropolitan area like San Diego. So you have to have some dark skies to see the rest of Capricornus. Oops, wrong way. There we go. Aquarius is the next sign of the zodiac over to the east. And Aquarius means it's a water carrier or a cup carrier. Despite both its prominent large size on the zodiac, it has no particularly bright stars. Like this constellation only has significance really because the sun does travel through it. And the water myth comes from ancient Egyptian astronomy here. Aquarius was associated with the flooding of the Nile. So when the banks were flooding, it was said that Aquarius was putting the jar into the water and causing the Nile to overflow, thus beginning spring. And so right now we're seeing Aquarius up at night. That means 6 months later, that's where the sun is during the day. And so 6 months from now would be spring. And so that's why it has that spring mythology associated with it. Now, this is the Pisces that you might have thought I had started to talk about earlier when I mentioned Pisces Ostrinis. This is Pisces, two fish connected together by a string. The brightest star in Pisces is located down at where the string or the tip of the V there. It is a star named Alresha. And then otherwise, it's actually, once again, a fairly faint constellation. The bright dot in it tonight, that bright red dot's actually Mars, and we'll talk about Mars again in a little bit. I'll show you a few images of Mars because, you know, I got to. And then the last sign of the zodiac over to the east, the one that's rising in the east at around 8:30 tonight, is Aries, the ram. The brightest star in it is named Hamal, and its star is located about 66 light years from our solar system. I don't know how you get a ram out of what looks like 3 stars all in a line, but that is it for the signs of the zodiac this evening. Now, I mentioned Mars. Let me put back up the zodiac with the 3 planets that are visible in the nighttime sky tonight. Mars, which is the brilliant red dot off in the east when you go outside at 8:30 tonight. And then 2 bright dots that have been going across the late summer and early fall evening sky close together have been Mars and Jupiter. So if you go outside tonight and you look for the 2 brightest objects after this show, the 2 brightest objects are actually going to be Jupiter and Mars. And then right to the left, I said that, just to the left of Jupiter is Saturn, the bright dot that you'll see there. So let's take a look at a few images of these worlds. And so that's what it looks like without the ecliptic up there. Now you'll notice the planets do fall along the ecliptic. The ecliptic not only is the path of the sun, but it also maps out sort of the shape of our solar system. Our solar system is flat like a pancake with all of the planets orbiting on a plane about the sun. And so that's what we're seeing when we see the planets along the ecliptic. So here is an image that I pulled from Kevin M. Gill's Twitter feed because he does amazing, amazing work. This is Jupiter from the Juno spacecraft as seen through sort of a fisheye lens. And this is not a rocky planet like the Earth. This is a big ball of gas, mostly gas. One of the goals of the Juno mission is to finally determine just how large the rocky core of Jupiter is. This is from the most recent perijove of the Juno spacecraft. And what we mean by that is that the Juno spacecraft is on an elongated orbit around Jupiter. So sometimes it gets really much closer to Jupiter than it is during the rest of its orbit, and it gets these fantastic images back. All of the imagery from the Juno spacecraft is available for you to play with on the Juno spacecraft website. And so go do some citizen science and play with the imagery of the Juno spacecraft. And then this is an image of this year of Saturn. This is an image by Damian Peach, who is an excellent astrophotographer, and he took this image of Saturn through a couple of different filters so that you can see that Saturn also has stripes going across it, but it's not as prominent as Jupiter's. So Saturn actually looks quite lovely through a telescope or binoculars this year. It's kind of got its rings tilted a little bit towards us that way. And this was the astronomy picture of the day today. And actually, yesterday. Actually, it was the astronomy picture of the day yesterday. These are sets of images by a photographer, Jonathan Grayson, who have been taking these images of Mars over the last several months. With the same telescope and the same camera, and you might be wondering, how can Mars get so much bigger? Well, last night, Mars was at its closest approach to the Earth this year. And so that's why Mars has been looking so beautiful and brilliantly red up in the sky. Mars has, so all of the planets have elliptical orbits. Most of the planets' orbits, though, are really close to circular, but Mars' orbit is actually fairly elliptical. So sometimes it gets closer to the Earth than others. And when it does get closer to the Earth, we see it better. So these aren't Hubble Space Telescope images or images from a spacecraft. These are images from an astronomer here on the ground who likes taking images of Mars. And I actually loved looking at images of Mars through sort of a backyard telescope because it shows you so much about Mars. You can see Mars has polar ice caps. From sort of the bluish fuzz in some of the images, you can tell that Mars has an atmosphere, but it's not a thick one, right? It's a thin one. And that it has features on its surface that we can learn about. And so that's Mars. Up in the sky tonight, a brilliant red dot. If the clouds cooperate, go outside and take a look at it. And so that's this evening's sky. So,
all right.
Okay. We're going to take a break for some of the questions?
Exactly. I think so, because some are for that section specific. So I thought maybe we could take some in between.
Okay.
So do you know what star constellations are found about 12 million light years away?
So in terms of the constellations, so 12 million light years away is so far away we can't see it with the naked eye. So we wouldn't associate any of those, we wouldn't have made constellations at that distance. However, when we look in these constellations with things like the Hubble Space Telescope, which can actually see millions and billions of light years away, there are things that distance in those and located in the direction of those constellations. Does that make sense? So basically every constellation up there is going to have stuff in it that's that far away.
Perfect. Thank you so much. And then we have a question about the name. So what does Zodiac mean and what does Capricorn mean?
So Capricorn refers to a sea goat. I don't know what a sea goat is. It's depicted in mythology as sort of half goat, half fish. Sea creature. We'll just call it a sea creature. And then zodiac, I don't remember where the term zodiac comes from, but it just actually refers to the region on the sky that the sun travels through. And so the constellations that go through that area are referred to as the signs of the zodiac.
Thank you. And then we're going to take one more, and then we'll get to the rest when we get to the Q&A. But how close is the star closest to the black hole to being ripped apart from tidal forces?
Ooh, that's a great question. So when you're looking at those stars whipping around the supermassive black hole at the center of the galaxy, you're probably thinking, wow, those look really close to be going that fast. They're still actually more than solar system size away from that central black hole. So if they were going to get torn apart, they probably already would have been, if that makes sense, because these stars, as you can see them whipping around, they still are on stable orbits. Stars that get close enough to get ripped apart by tidal forces wouldn't have lasted many passes. And so since our galaxy is several billion years old, most of the objects that would have gotten torn apart by tidal forces probably already have been. But we can still nudge some stuff towards the galactic center. Stuff can get tugged in that direction. But yeah, I don't think we have any evidence that any of those particular stars are being torn apart. We have seen stars get torn apart by black holes, but I don't think any of those ones that we were looking at in there have been those.
Thank you, Lisa. And then we're going to get to the other questions after your presentation on the life cycle of stars.
All right. So there's one star in our solar system, and that's the sun. And the sun is a fairly average or typical star located in the gravitational center of mass of a system. It's held together by its own gravity, which means, well, actually, let me put it this way. It's powered by nuclear fusion at its core. That's its energy source. And so if it's basically a big fusion reactor in the center, so what's keeping it from blowing apart? Its own gravity. So during your typical life of a star, gravity pulling inward is being balanced out by radiation pressure pushing outward. And so that is a typical star. The other aspect of it being a typical star, it's made mostly out of hydrogen and some helium. So if I want to determine how stars form, the first thing I have to ask myself is there hydrogen out there to make stars from? Like, are there still reservoirs of fuel to make stars? And so the answer is yes. All of these dots that I have put up here now, all of these symbols on the sky, are the locations of nebulae. Different types of nebulae, but nebulae nonetheless, where a nebula in astronomy is defined as a huge cloud of gas and dust where that cloud is mostly hydrogen. And you'll notice that most of them fall along the Milky Way. And basically, this is showing us the shape of our galaxy. Much like our solar system is flat like a pancake, so is our galaxy. And we're seeing the plane of that pancake, and we're in that plane ourselves. So the answer to the question, is there hydrogen out there to make stars, is yes. And so here is a close-up image towards the center of the Milky Way in color. Everything that looks like a whitish bit of fuzz is actually so many stars so close together you can't tell them apart. So the whitish stuff here is starlight. The reddish regions, the bluish regions, the yellowish regions, and the brownish black regions, those are all huge reservoirs of gas, mostly hydrogen gas, and then some helium. And so there is a lot of gas out there still to make stars. So let's talk about those reddish pinkish regions. They're called emission nebulae because uh, they show something that astronomers refer to as an emission spectrum. So they look like a hot gas to our eyes, and that's actually what they are. You might notice that there's a lot of stars towards the center of this nebula, and the heat, the energy from those stars actually is heating up the gas and causing it to glow. And that's awesome because if I have a heated thin gas, I can take a look at its light and tell what it's made out of. And so this is mostly hydrogen. And this is another example of an emission nebula, also mostly hydrogen, because hydrogen glows red to the naked eye. And so these are images of nebulae, what they would look like to the eye if you could detect them. The bluish regions are called reflection nebulae, where they're not actually reflecting light, they're scattering light. And they have this bluish color, much for the same physics reasons that our own sky is blue. So this particular nebula is made out of gas and dust, mostly hydrogen gas. Now the dust that we see out in space isn't the dust like is in your home, because the dust in your home is mostly you, right? It's skin cells and stuff like that. That would be awesome out in space, but that's not what we see. And so we're talking about little bits of carbon, little bits of iron, little bits of silicates. And the smaller the size of the particle, the shorter of wavelength of light that they scatter. And so that means that light hits it and the light bounces back off. Preferentially, the light that bounces back off is blue light. And so what we're seeing here, you'll notice that there's lots of blue stars in the vicinity of this object. Well, that's why this particular object is scattering blue light very vividly. I picked this reflection nebula to show you since it's October and a lot of people get excited about Halloween. This one is called the Witch Head Nebula. This is another example of a region that has a couple of reflection nebulae in it. So once again, you're seeing that blue light being scattered by the dust particles in the nebula. But you'll also notice a couple stars that look like they have sort of a yellowish gas surrounding them. That's actually also light scattering. But those stars are red stars, and they don't have a lot of blue light to scatter. So what we're seeing here is the shortest wavelength light getting scattered that the star has in abundance. And so occasionally, very rarely, we actually do see yellow reflection nebulae. And then there are dark nebulae out in space. And these are dense regions of gas, once again, mostly hydrogen gas and dust particles. These regions are also sometimes called molecular clouds. They are the coldest, densest regions of space where molecules can actually form. Now, they're not that dense, though. The densest region of space would still be emptier than the best vacuum chamber we can build here on Earth. It's just, they're huge, and I'll give you a feel for that in a few minutes. Now, what I love about these is that when they were first discovered after people started being able to use the telescope to look up at the sky, these regions in some places were so dark that it was thought that they might be true voids in space, like regions where there were no stars whatsoever. And it's really fascinating to look at them with the eye, because when you take a look through a telescope, when you're actually looking out through the eyepiece and you're looking at some of these dark nebulae, you can feel your pupil dilate as it's trying to get enough light to detect. It's a really weird feeling. You can feel your eye kind of stretching to see. But now we know that they're not true voids in space, that there's stuff there. Now, why can we see such detailed images of these nebulae? Because they're absolutely huge. This is an image of the sky taken through a hydrogen filter. So you're picking up the light of the hydrogen gas. And you can see prominently right there above the house is the constellation Orion. And so if you could detect these nebulae just with your eyes, they'd be everywhere. And so sometimes I have students ask me, it's like, Dr. Will, why can you show me such detailed images of nebulae, but you can't get me a good picture of Pluto from the Earth, right? And Neptune just does not look good from the Earth. And they're so much closer, but they're so much smaller. These objects are far away, but they're huge, absolutely huge. They're so far away that we don't pick it up enough light to detect them with our eyes. But if we have a camera up to a telescope that we can leave the camera shutter open, in some cases for hours, to pick up the light, we get these beautiful images. And that's important because stars start off in those dark nebulae. And so our idea of how star formation occurs, to start off the life of a star, is that we have this dense region of gas and dust that is spinning, and it collapses under its own gravity, and it fragments into all sorts of different bits, and each of those fragments continue to collapse under its own gravity until you eventually have a star, something called a protostar, because it's not doing nuclear fusion yet, it's still heating up, surrounded by a disk of material. And it's in that disk of material where you can possibly make planets. And we think stars and planets form at the same time out of the same process. And so these are not two different processes, they're one process, but we're not going to focus on the planets tonight. But it takes a long time for this to happen. So for me to try to convince you that this happens, I have to show you the individual bits. I have to show you clouds of gas, mostly hydrogen, out in space, that look like they're forming little fragments and maybe with disks around them. So this is my favorite dark nebula because I have a favorite of every type of astronomical object. And I think you can see here why they thought at first that these could be voids in space. Because the center of this is not showing any light, invisible light. But you'll notice around the edges of that dark nebula how coincidentally all the stars seem red. That's because only the longest wavelengths of light are getting through. So we're seeing the red light because the blue light's been scattered away. And so those stars are red for the same reason that sunrises and sunsets are red. And then the stars behind this cloud, there's so much material there that starlight can only get through the less dense outer edges of the cloud, and the stuff in the middle can't get through. So are there huge regions of gas and dust out in space ready to form stars? And the answer is yes. And do we see them forming fragments with bright dots in the middle that might be these protostars? And the answer once again is yes. And all of these are just from the Orion Nebula in the constellation Orion. All of these little protoplanetary disks and protostar forming disks. So we actually can see these. Usually we take a look at these in infrared light because star formation occurs deep in these clouds of gas and dust, and it's easier to see through in infrared light than it is in visible light. Here's another set of basically what we call young stellar disks. We have the protostar in the middle that's starting to blow away some of the gases the planets are forming in the disks. And then what I was just mentioning about infrared being easier to see through, these are all Hubble Space Telescope images of a nebula in the constellation Carina. And I want you to focus at first at the top two images. The one on the left is in visible light. When I say invisible light, it makes it sound like I'm saying invisible. I know. All right. So the one on the left is taken in the light you can see with the eye. Let's put it that way. And then the one on the right is infrared light. And it's the same image, just the same region to scale. And you notice how you can see a whole bunch more stars in the image on the right? That's because those are the stars that have been forming deep down in that cloud of gas and dust, and the starlight's getting through in the infrared, but not in visible light. And so this is the image that the Hubble Space Telescope released for its 20th anniversary back in 2010. And what we're seeing down in the bottom images are regions where stars are forming, and as they heat up, they actually start ejecting jets of material away from them. And you can see the size scales down there. We're looking at things on order of light years across. And then this is a close-up of this image. This is the textures there are amazing. This region is located about 7,500 light years from Earth, and the pillars up top measure about 3 light years in height. And so absolutely huge regions of space, which is why I can show you details of them and not Pluto from here. So this is an active star forming region. And then after the stars are formed, the stars heat up the leftover gas around them, causing it to glow. And so here's another classic emission nebula. This one's called the Rosette Nebula because it looks like a rose. And the stars in the middle are a newborn cluster of stars, still heating up the gas that was left over from their formation process. And I know that those are young stars because they're blue. The bluer the star, the hotter it is, the faster it burns through its fuel. So blue stars, if you see a blue star in the sky, by definition, it is young because it doesn't live long enough to get old. So this is a young cluster of stars. And then the high energy, particularly the ultraviolet radiation from these young stars, actually will push away the gas, leaving behind something we call an open cluster. And so this is a young cluster of stars. At one point, our own sun was likely a member of one of these, but they're several light years across. And then as this open cluster orbits the center of our galaxy, the stars closer to the center of the galaxy will orbit faster, the stars further away will orbit slower, and these clusters get pulled apart over time. And so that's another sort of tidal breaking up of a cluster. Getting back to the question about the black hole and the star earlier, we can actually break up entire clusters of stars. The individual stars and solar systems are fine, but the entire cluster can drift apart due to that difference in gravity on either side pulling on them. So we formed stars. They live their lives burning hydrogen to helium in their cores. But there comes a time when at the very center of the galaxy, at the very center of the star, all of the hydrogen turns into helium, and it's not hot enough and dense enough to fuse helium there. So the core of the star starts to collapse under its own gravity because there's no nuclear fusion supporting it anymore. But as that core collapses, it heats up and it causes the outer layers to expand. And then these stars go through phases that we call red giant phases, and then eventually they blow off their outer layers. Now, whether or not they blow off their outer layers gently or with a bang depends on the size of the star. So if you're a low mass star like our own sun, you will fuse hydrogen into helium, helium into carbon, and then you will blow off your outer layers and become something that's called a planetary nebula, which is one of the worst names, quite frankly, in all of astronomy because it has nothing to do with planets. Where the name comes from is that the first planetary nebulae that were identified were because astronomers were looking at these through small telescopes back in the late 1700s, early 1800s. They were looking at these through small telescopes and said, hey, those nebulae look round like a planet. And that's kind of the historical origin of these names. So the previous one was the Helix Nebula in the constellation of Aquarius. This is the Ring Nebula in the constellation Lyra, which is up there in the Summer Triangle. To give you a sense of scale, it's about 1 light year across. And then one of my personal favorite planetary nebula is the Cat's Eye Nebula up in the constellation Draco, located about 3,000 light years from us. And I like this one because the other ones definitely looked round like a planet, but this one has a little bit more of an intricate structure to it. There's some exploration of the idea that there's more than one star down there, and so the other star is helping to basically change the way the outer layers are moving away from the star that has evolved and has blown off its outer layers. And if you've been looking carefully, you may have noticed all of these images had white dots at the center. Those white dots are what we now refer to as white dwarfs. The brightest star that we can see in the evening sky ever from our Earth is Sirius, up in the constellation Canis Major, visible in the wintertime. but it has a small object next to it in orbit around it that you can't see with the naked eye, but we call it Sirius B here. And it's the first white dwarf that was, actually it was the second white dwarf that was ever discovered, and it's the closest one to our own Earth. So it's one of the best white dwarfs that have been studied. And so what happens is, for a low mass star like the sun, when the planetary nebula occurs, the outer layers of the star get blown off, but the core of the star is left behind. And this core is mostly carbon, and and it's only about the radius of the Earth, but it can have about the mass of the sun in it. So it can still be really massive, but it's small. So it's really high density, and it's shining by uh, leftover heat, because it's not actually producing any more energy. And so this is an artist representation of the star Sirius and its white dwarf companion. And then this is an example of an incredibly young planetary nebula around a white dwarf star. You can see that the dot in the middle here is still really close to the outer layers that it's thrown off. This is possibly the hottest known white dwarf because it is one of the youngest ones we've seen, one of the earliest in its formation. So this is actually the eventual fate of our own sun. In about 5-6 billion years or so, we are going to have expended all of the fuel that we can by fusion in the core of the sun, and then the outer layers will gently blow off of the sun, leaving behind this incredibly hot, highly energetic, exposed core known as a white dwarf. So you've heard me refer to the term high mass or low mass star, which implies by definition there must be a high mass star. And so the cutoff is about 8 times the mass of the sun. And where that cutoff comes from is we have to ask ourselves, well, what can a high mass star do that a low mass star can't? And what it can do is it can fuse carbon. So stars all start by fusing hydrogen to helium, helium to carbon. And then if it's a high mass star, it goes carbon to oxygen, oxygen to magnesium, magnesium to neon. It goes through a whole other cycle all the way to iron. And once it fuses iron in its core, we have this incredibly small, hot, tiny, compact core. But you can't fuse iron naturally because it takes more energy to bring the iron together than it produces. So it's not a naturally occurring fusion reaction. So this core basically collapses. All of its iron breaks down into its components, protons, electrons, and neutrons. And it forms this incredibly dense core, and it blows off its outer layers, becoming something called a supernova. And this is a violent explosion. It's not sort of the let's blow off the outer layers of the sun. This is a violent explosion. And you can get sort of a sense for it here. This is a during supernova image on the left and an after on the right of supernova 1987A, which happened in a nearby galaxy called the Small Magellanic Cloud. It's actually a small galaxy that orbits our own Milky Way. And this is the closest supernova that's happened since this Hubble Space Telescope was launched. And this is the first supernova that was easily visible from the southern hemisphere for several hundred years. There's been a more recent image I wanted to show you of a supernova. So whereas supernova 1987A was located just a couple 100,000 light years away, this is a supernova going off in a galaxy that is located about 70 million light years away. And what you can notice here, this is a time-lapse set of images from the Hubble Space Telescope. This is a star that we saw go supernova in 2018, and then it was observed from 2018 into 2019 so that you can see it taper off in brightness. At its peak, this exploding star was as bright as about 5 billion suns. And so a supernova can actually outshine the galaxy that it is in briefly. And then supernovae make beautiful explosions and they make pretty pictures. This is a region of the sky up in the constellation Vega where about 12,000 or so years ago, we estimate a supernova exploded and caused this supernova remnant that we see over in the right-hand part here. I always, when I say over in the right-hand part, you can see where there's a region where you see a lot of blue stars and not as much gas. That's because the supernova explosion has pushed the gas out of the way, clearing it out and triggering star formation. You can actually see that sort of ring of blue stars where the supernova shockwave has gone through. This is one of my favorite regions of the sky. I actually remember seeing an image of this part of the sky when I was a little girl and wondering, how can that be so pretty? This is what it would look like in visible light. Perhaps the most famous supernova is the Crab supernova, which occurred in the year 1054 AD from our perspective. It was so bright it was visible during the day. And now, almost 1,000 years later, when we look at this point up in the constellation Taurus, we see the leftover remnants of the star exploding and still moving away at thousands of miles per second. This nebula was the first astronomical object identified with a historically known supernova explosion. And deep inside of it is something that we call the Crab Pulsar. The images on the right is a time-lapse image from the Hubble Space Telescope, on the left from the Chandra X-ray Observatory. And there is a pulsar that is still so energetic almost 1,000 years after its creation that it's still pushing the gas near it away from it. And so there's still energy involved here in the Crab Nebula from its explosion. And I called it the Crab Pulsar. What's a pulsar? Well, when high mass stars die, they can become, their cores, well, the outer parts leave as in a supernova explosion, but their cores get left behind. And there's two options for what they can be, something we call a neutron star or a black hole. And the Crab Pulsar is an example of a neutron star where we see jets of light emanating from it due to its rapid rotation. Pulsars were discovered in 1967 by Jocelyn Bell, who should have been one of those women who got a Nobel Prize in physics for the discovery, but she didn't. Her advisor got the Nobel Prize for this one. So we're just going to mention that today. She discovered pulsars, which were the experimental evidence that neutron stars actually did exist. Neutron stars are tiny. They're only about the size, say, of an asteroid in our solar system, but they contain between 1.4 and 3 times the mass of our own sun. This is an all-sky image in gamma rays of some known pulsars, and so you can see that pulsars also fall along the plane of the galaxy. And then if the leftover core of a high-mass star is greater than 3 times the mass of the sun, we have predicted that it should make black holes. And this is a set, it's called Masses Here in the Stellar Graveyard, which is a very fancy way of saying these are all of the black holes that the LIGO and Virgo gravitational wave observatories have directly detected the gravitational waves from. So I made this graph today up because the data was updated just last month in September. And so you can see that we have directly detected black holes of sizes made by the deaths of high mass stars. So the life cycle of stars, they form in nebulae, the star evolves, and they create nebulae afterwards. But some of the mass that gets left behind is always trapped in those cores, and they can't go back into making more stars. But to a certain extent, stars recycle. And that's the life cycle of stars, which I like to call pretty pictures and explosions. Pretty pictures and explosions.
Exactly. Perfect. All right. We're getting close to 8 o'clock, so which is normally the time we end.
Okay.
But we have many questions, so I know we're going to go over a little bit. If you want to stay with us, that's great. If you have another commitment at 8 o'clock, please do not feel bad for logging out. We understand. But we're going to go to some questions. Lisa, you ready?
I am ready.
Awesome. Okay. Karen is asking, the New Horizons spacecraft recently took a photo of Alpha Centauri, which showed the increased parallax from its viewpoint. Has any proposal been made to launch a spacecraft toward the outer solar system to measure distances to nearby stars more precisely?
So that is an awesome and fantastic question, and I wish the answer was yes. So because that is what we would really like to be able to do, because basically if parallax is the apparent change in position of an object based on the actual change in position of the observer, and if you know the change in position of the observer, like in between your two eyes, you can use that as the base of the triangle and get the height of the triangle or the distance by geometry. And so if we actually had a bigger base, like putting a spacecraft way out there so that we could triangulate with it, that would be awesome. But we don't really have that capability. The New Horizons spacecraft is as far out as it is because we launched it really, really, really fast. And so trying to put it into an orbit where it would be more stable so that we would know its position to good amounts, or to have a mission just devoted to that, wouldn't be the most effective usage of our resources, but it's a really awesome idea because it would actually really help us in our capability to get distances better.
Well, we'll propose it to NASA. How about that?
We'll do that.
Yes. Before I get to the next question, I just opened the poll. We always like to survey our audience. So while you listen to questions and answers, take a moment, please, to fill out that survey. That would be wonderful. Thank you very much. Next question. Each planets, or all the planets, have their own amount of gas. And what kind of gas does planets like Jupiter and Saturn have?
It's a great question. So when we take a look at the planets in our solar system, Jupiter, Saturn, Uranus, and Neptune are mostly hydrogen and helium, like almost entirely hydrogen and helium in their outer layers. Whereas Mercury doesn't really have an atmosphere, or not much of one. Venus and Mars both have mostly carbon dioxide and nitrogen atmospheres. It's just the Martian atmosphere is much thinner than the Venus one. And then the Earth is a nitrogen oxygen atmosphere. So the terrestrial planets have some variations in their atmospheres. Now, the biggest variation in our atmosphere, though, is probably the fact that the Earth is in the habitable zone and life formed here, and that the oxygen in our atmosphere is probably mostly due to biological outgassing. So we are in an atmosphere that life has already altered, which is something to remember the next time somebody says, well, people can't really affect the atmosphere with carbon dioxide emissions. The answer is yes. Yes, life can alter the atmosphere. We've done it before, just in different ways. So yeah, every planet has a characteristic atmosphere, and the four Jovian planets are the ones that are most similar to each other.
Thank you. And then how will Juno determine the size of Jupiter's core?
The way that so the Juno spacecraft has multiple instruments on it, and one of them being a gravitometer. And so when you're in orbit around an object, you can sense its tug of gravity. Like when we would put things in orbit around the moon, we could actually determine what they called mass cons, or mass concentrations, places where the mass was a little bit more concentrated, basically density differences on the surface of the moon, because you had to fight harder to keep your orbit. And so similarly, if you have a gravitometer on a spacecraft, you can do that. So it's going to try to map out the shape and position, and so basically sort of the density of Jupiter better on its inside. Then it also has things like magnetometers and stuff like that that'll help too, but the basically just looking for the mass distribution in Jupiter.
Fascinating.
Yeah.
And then somebody would like to know what stars can be bigger than our sun?
What stars can be bigger than our sun? A lot of stars can be bigger than our sun. Our sun actually is pretty average. There are stars smaller than us, larger than us, hotter than us, cooler than us. So we're actually, that makes us sound boring, but what it means, we're a great laboratory. So if we understand the sun, we should be able to understand stars. But when you look out into the sky, a lot of the stars that you are looking at are bigger than the sun because those are the brighter ones typically.
That makes sense. Okay, the stars that are close together. Sorry. Does that mean planets that look like stars from the telescope are close together?
All right. So when we take a look at stars, and so I'm trying to parse the question. I'll answer it a couple of different ways.
Okay.
So stars that look close together through a telescope, they're still like so many light years apart from each other, right? You know, so the distances between stars are still pretty big. If there are planets around those stars, those planets are so close to those stars that from our perspective, we can't see them because they're lost in the starlight. So if you were like 5 light years away looking back at our solar system, you wouldn't see us, you'd see the sun, because we're so close and so small, we're lost in the starlight. Much like it's hard to see the planet Mercury even here from the Earth, because it's so small and so close to the sun, we have to catch that in the right conditions. And so we usually look for planets not from their light, but from how they gravitationally affect the star, or how they block out some of the star's light when they pass by it.
Perfect, thank you. And then you showed one of the nebulae. It was called Witch Head. Do you know why it's called Witch Head?
Because of its profile, it looks like the witch's head from the side, I guess.
Makes sense.
You know, like the Crab Nebula doesn't look like a crab if you look at it through a good telescope. So but the witch's head, if you look at it, you can tell.
You can see it. Okay.
Yeah. Sometimes that shows up as the astronomy picture of the day on Halloween.
Yeah, that makes sense. Perfectly fitting.
Yeah.
How can astronomers talk about seeing light from galaxies close to the time of the Big Bang? Shouldn't that light have left the universe billions of years ago?
First of all, hi Scott.
Hi, Scott.
Scott is a classmate of mine back when we were undergrads at UCLA, believe it or not.
Yay!
Recognize that name. And he has attended planetarium shows at the Fleet before, even though he does not live in San Diego. So so when we take a look at galaxies 12 billion light years away, which the Hubble Space Telescope has detected light from telescopes that far back in time and that far back in distance. The universe is big. And so the universe is bigger than that 12 billion light years. The universe has expanded faster than the light travel time, because the universe is not bound by the laws of physics inside the universe, which is a separate issue. But yeah, don't.
Yeah,
but
that's going to make my head explode.
Yes. But the idea is that I like to think of light now coming from distant stars and distant galaxies like buffering video. So the galaxy is 12 billion light years away. And so if a star turned on in that galaxy, we don't see it now. We have to see it 12 billion years after it turned on. But once we start seeing it, that we get that light continuously. So some of you may have heard that some of the stars up in the sky might not even be there anymore. How can we still see them? Because it had that buffer, right? That light has been traveling to us, that even though someone may have turned off the off switch now for that star, its light is still traveling to us. So hopefully that helps answer. The light has a long way to travel in the universe.
And that brings us to another question that was asked. Can you please explain light year?
Okay.
For us.
So, yeah. So light year, you always have to tell me to explain that, because astronomers get really used to it. So the light is the fastest that anything can travel in the universe, as far as we know. The laws of physics as we currently understand them, correct? And so a light year is defined as the distance that light can travel in a year. So really, really fast for a decent chunk of time is a really big distance. It's so big that I don't think it's actually useful to try to give you a number in miles or kilometers, but let me give you some smaller distances to wrap around. Our closest celestial neighbor is the moon, and in light units, it's 1.3 light seconds away, because it takes light 1.3 seconds to get from the moon to us. So even looking at the moon, you're not seeing it as it is. You're seeing it as it was 1.3 seconds ago. The sun is 8.3 light minutes away. And those are both objects in our solar system. And so you can imagine now that a light year gets us way outside our solar system. In fact, our solar system is about a few light hours across.
I thought it was light years.
Oh no, we're tiny.
Yeah, clearly.
We're tiny.
Peter has a fun question. If Betelgeuse? I never quite know how to pronounce it.
Betelgeuse.
There you go. Thank you. Goes supernova in our lifetime. apologize, not my language. If it goes supernova in
That's
our
good.
lifetime, it will be amazing to see. But what will astronomers do to adjust the shape of the constellation Orion?
Oh, it'd be worth it to have to adjust Orion for this. You know what's really funny is that for the most part, this is how rare supernovae are, that I cannot think historically in the 2000 years that we've had that 48 constellation catalog of Ptolemy, I cannot think of a constellation that has structurally had to be changed because it lost a star due to a supernova.
Hmm.
In fact, the star itself, the supernova, will be really, really bright. It'll take about a couple hundred days or almost a year to go back down to the original light level because supernovae can be so bright. And then the region around it, when it's making that supernova remnant, can actually have sustained brightness for long periods of time. So there would still be something there. It would give us time to talk about what to have to do. But I honestly can't think. We've changed what constellation stars belong to over the years, but I can't think of one that we've done it because, oh, we had to, because, oh no, there's not a star there anymore. I don't think that's happened. So great question, though.
Yeah, it's a good one.
I
Hey,
like it.
Peter, by the way.
Yeah. Hey, Peter.
And then we have some questions about the gases in the universe. So we've heard you mention hydrogen quite a lot.
Mhm.
So how much hydrogen and how much helium?
It's about a 90% hydrogen, about 9% helium, and then everything else is in really tiny amounts. But that's about the ratio, 90 and 9. Yep.
All right, that's a lot.
Yes. Oh,
Okay,
yes.
go ahead.
I was just saying we're not much like the stuff that makes up the carbon, the calcium in our bones, the iron in our blood actually is fairly rare.
Yeah,
And when you think of it on that scale.
perfect. So we have one last question, and then we have to call it a night tonight. Clouds here and in the universe, does it make a difference on light years, how fast light can travel?
Right. So some of the nebulae that we were looking at tonight are light years across. Like your typical emission nebula is about a handful of light years across. You can think of it that way. Like say anywhere from like a handful to a dozen is a typical emission nebula. If you're talking about things like the Oort cloud around our solar system or the Oort clouds that probably exist around other systems, we're still on order of light hours to light months, maybe, like there's still the distances between stars are huge. Another way to think about it is that the closest star system to our own solar system is the Alpha Centauri system, and that's about 4 light years away, a little bit over 4 light years away. So even things like we refer to as cometary clouds are really close into our solar system on that scale.
Perfect. Thank you so much.
Thank
And
you.
that concludes our night tonight. Leah, stay on. I will send you a little message in a second, so please don't go. But I want to thank everybody for joining us tonight for another great Sky Tonight presentation. And I hope you'll join us again next month when we look at comets and meteor showers. That'll be fun. Is there anything coming up that we need to look at in the sky that we're talking about that?
So in November of every year is the Leonid meteor shower. So I always like to talk about the meteor showers on a month when you might have a chance of seeing a good one.
Awesome. Perfect. Great. Then I hope we will see you all again next month.
Bye, everyone.
Bye.